We're going to start today's lecture with section 13.6 in your organic chemistry textbook. So again, this is the McMurray textbook, the new one, organic chemistry with 8 applications, with the organic chemistry 8th edition. And section 13.6 starts by talking about carbon-13 NMR spectroscopy. So we've introduced that during the lecture on Wednesday, February 4th. And now we're going to talk in more detail about sort of specialty information that we can get from doing this carbon-13 NMR spectroscopy. And in particular, we're going to start by discussing what's called DEPT, D-E-P-T, C13 NMR spectroscopy, and that stands for distortionless enhancement by polarization transfer. It's a technique, it's a pretty specialized technique really, but what this does is it allows us to look practically in terms of figuring out what our molecule is. It allows us to get extra information about the carbon, the different carbons in the molecule, by sort of irradiating them at under different conditions, and then using that information again to get information about the substitution around the carbon atoms. And in particular, what people usually do when they're trying to do these depth experiments is they do a series of experiments. So first they'll take a regular carbon NMR spectrum. First you get a regular carbon spectrum. That's the first one. And what that does is it gives you a signal, a unique signal for every unique carbon atom in the molecule. We've already talked about what I mean when I say unique. And then they run a series of further experiments. They do a DEPT90 that shows only signals for carbons that have one proton attached to it. So if you have a CH3 or a CH2 or a C with nothing else, a quaternary C, then you see no signal in that particular spectrum. Following that, they run the spectrum called the DEPT135. That's the third carbon-13 NMR experiment that they run. And in those cases, what you end up seeing is a positive signal for a CH3 and for a CH. You see a negative signal for CH2, and you see no signal at all for the quaternary carbons. So I'm going to do an example of this, but again, what we usually do is, in addition to getting sort of the general information from a regular carbon NMR experiment, you can run the regular C13 NMR, then the DEPT90, then the DEPT135, and really get a better sense on what is the substitution patterns of the particular carbon atoms in the molecule. So let's now look at a specific example of that. So if I look now at this compound here, this is isobutyl acetate. We're going to talk about ester nomenclature when we get to that a little bit later on in the semester. But if I look now at this isobutyl acetate, and I start to ask myself what are the different types of carbon atoms in the spectrum, I can see, well, this is certainly one carbon atom, and this one, 1, 2, 3, 4, 5, and then these two CH2s that are coming off of the CH, those are chemically equivalent. I'm also going to draw the ChemDraw for this isobutyl acetate just because it's often easier, at least for me, I don't know, for you guys, but hopefully for some of you at least, this kind of depiction will help us figure out a little bit better what's going on in this molecule here. So let's see what this compound looks like. If I draw it like this, it becomes hopefully a little bit clearer to us how many different kinds of unique carbon atoms there are in this molecule, where certainly this guy, the carbonyl one, the one closest to the ester, this one labeled D, this is A over here, and then these two guys, these methyl groups are chemically equivalent. So here they've labeled those A, B, C, D, E, F, and A, B, I don't know why that one's C, A, B, C, D, E, F, those are the different carbons in the molecule. And if I just take a regular carbon-13 NMR spectrum, I'm going to see unique signals for each of them, and you can see the carbonyl one, so that F is way down here at around 170 ppm, and we've already talked about that. And the one that's closest to the carbonyl on the other side, so this E carbon, is further deshielded, so this is around 60-ish. And then you have a bunch that are in the normal alkane region. So that's as far as information you can get from this spectrum as well. I have no idea what that was. Sorry, guys. And now what I can do is run a depth spectrum over here. So this is a depth, hold on, which depth is this? This is a depth 135 spectrum that they've run for this particular compound. And you can see now the carbonyl, so that has no extra protons attached to it. You're seeing no signal at all for that in the depth spectrum. Now the ones that are CH2, so that's E and D, those show up as negative, and the ones that are either CH or CH3s now show up as positive. So this is the kind of useful information that we can get from this, in this case, this depth 135 signal. We can do another example as well. So this one you're seeing a regular carbon one over here, got quite a lot of stuff. A depth 135, so the CH3s are positive, the CH2s are negative. And then the depth 90 gives us CH, which is only CH ones, and those are all showing up as positive. So this is actually quite useful information, as we can see from these two examples, in terms of what structural information, what more information we can get from these carbon atoms, from these carbon spectra, just from running this series of depth carbon experiments. We're going to do one more example together in terms of figuring out what we can get, whether we can actually get a chemical structure, a complete structure just from a carbon-13 NMR experiment. So let's look at this here, this worked example here. So if I have an aliphatic alcohol with the following chemical formula, C4H10O, and this is its NMR data. It has it has 3 signals, okay. Depth 90 shows me 1, and the depth 135 here shows me a positive at 19 ppm and a negative at 69.5. So the first thing I'll figure out is that because I have a C4 but only 3 signals in my carbon NMR spectrum, the first thing I can figure out is that there must be 2 of these carbons must be chemically equivalent. Okay, the second thing is I can see that the 19 and the 31, those are pretty close to the regular alkane region, saturated alkanes. That 69.5 is going to be the one that's bound directly to the OH, that electronegative atom. And then what information I'm going to get from the depth 90 is I can figure out that depth 90 shows me only signals for CH carbon atoms, so then I can see that I have one that's a CH. Depth 135 now shows me that the positive one at 19 is a CH3. Okay, and the negative one, because I didn't see that in the depth 90, that's how I know it's a CH3 in general. The depth 135 will show positive for CH or for CH3. So this one I'm going to see is a CH3, again because it didn't show up at all in the depth 90. The negative peak at 69.5 ppm shows me a secondary CH2. So now I can figure out probably that my structure has 2 CH3 groups here bound to the same tertiary CH carbon. And I can put that information all together and draw a structure that looks like this. So these are the 19 ppm carbons. This is a 31.7 ppm carbon, and this guy over here, this CH2, is the 69.5 ppm one. And that's pretty conclusive in terms of determining the structure. We're going to move from here now and start talking about proton NMR spectroscopy. So this is again section 13.8 in the book, and the same basic principles for proton NMR spectroscopy apply. So just like in carbon spectroscopy in C13 NMR, we saw that each chemically distinct carbon, here I'll write this, distinct carbon gives its own chemical signal. Same thing in the proton NMR spectroscopy. Each chemically distinct hydrogen atom is going to also give us a unique signal in the spectrum we can use, but there's also a fair amount of other useful information that we can get from a proton NMR spectrum. Basically, proton NMR is the single most useful spectroscopic technique for trying to figure out structure. So let's ask ourselves now, what information can I get from a proton NMR spectrum? The first thing, and this is what we're going to talk about right now, is how many distinct types of hydrogen atoms are in my molecule. So let's talk more about what I mean by that. In general, if you're not sure, so sometimes with a simple molecule, I can just look at that molecule and figure out right away how many distinct protons and chemically equivalent protons there are in the molecule, but it's not always so easy to say. So what we can do, and your book again goes through this in some amount of detail, is actually do a little exercise where if I look at two protons and I'm not sure whether they're equivalent or not, I'm going to replace each one sequentially with an X group and then see if replacing them with an X group gives me the same molecule or two different molecules. So how do I figure out what is chemically equivalent? I can look sometimes, or I can replace the two atoms in question with an X group and then see if that gives me the same molecule or two different molecules. So let's do an example. So let me pull up the ChemDraw here about this. So now here I'm looking at this molecule. So this is N-butane, a simple alkane. And my question now is this H, this blue H over here, the same chemically equivalent to the green H? So to do that, what I'm going to do is replace this green H with an X, and then separately replace the blue H with an X. So I end up with this structure and that one. And then I can ask myself, well, are these the same compound or are they different compounds? So it's clear now that a compound with the X with the halide on the terminal carbon is not at all the same as the one which has the X on this one of these internal carbons. So, which means then that this blue H and this green H are distinct and they are not chemically equivalent. So here I can say that the products when I put the X into the molecule are not the same. And that means, therefore, the two protons are not chemically equivalent. So that's the first choice. When I'm trying to figure out if they're chemically equivalent or not, I have four different possibilities. Let's put that back in these notes here. There are four possibilities. Possibility A is that the two protons are different. Good. Possibility B is what I'm going to show back in this ChemDraw file, is if I look at all of these blue protons and I replace any of these protons, any of these hydrogen atoms with an X, that's going to give me exactly the same alkyl halide product shown over here with the X on the terminal carbon. So any of these H's will give me the same halide product. That means that these H's are all chemically equivalent. We call them, those protons then, homotopic. So if the two protons are chemically equivalent, those are called homotopic, and they give me only one signal in the NMR spectrum. I now also, so you may think those are my only two choices, they're either the same or they're not the same, but it turns out that that's not quite true. So I have two other choices for this. So we have two other options as well, in addition to our compounds being different or identical, even though those are the two obvious ones. And the third choice here is what are called enantiotopic. So I'm going to show you an example of what I mean by that in this ChemDraw file. So if I look at this ChemDraw file here, and this particular structure, this H, green H and blue H, those are identical protons right now. There's no chemical inequivalence, but, and here's the subtlety, if I replace the blue one with an X, that gives me an R configured chiral center. And if I replace the green one with an X, that gives me an S configured chiral center. So these atoms are called pro-R and pro-S hydrogen atoms. And if I replace those with each of those individually, what that gives me are two enantiomers. Okay, so these are not identical. They're similar, but instead of seeing identical molecules when I put in my X's, I actually see enantiomeric molecules. That means that these protons are called enantiotopic, these hydrogen atoms, sorry. And again, enantiotopic means that if I replace either of them with an X, I get, instead of identical molecules, I end up getting enantiomers. So that's my enantiotopic case. Replacing each hydrogen atom with an X will give me enantiomeric products. My fourth choice is even a little bit more subtle than that, and this is something that's called diastereotopic. So diastereotopic atoms, hydrogen atoms, are only seen in cases where there's a chiral center already in the molecule. I'm going to write that here as well. Only seen where there is a chiral center already existing in the molecule. And if I look here at this compound shown here, here's my chiral center. So I'm not focusing on the chiral center now to determine my diastereotopic hydrogen atoms, but I'm looking at a molecule that has a chiral center in it, and I look at the green H and the blue H, and here if I replace the green H with an X, or the blue H with an X, what I get are not enantiomers, but I actually get diastereomers. So I'm not changing this, what's happening at this particular center. What's happening at these centers, this particular carbon is the same thing that happened here. I'm getting enantiomeric centers at that carbon, but because I have a separate chiral center already in the molecule, what that gives me instead of enantiomers is it gives me diastereomers. Just to review, so we're all clear about this, diastereomers are stereoisomers that are not enantiomers. So in this case, I have a molecule with two stereocenters. One of them is identical in both cases, and one of them is enantiomeric. That means that these products are diastereomers, and that the blue and the green hydrogen atoms are therefore called diastereotopic. And this is not obvious at all. It's really only something that you would see if you started actually putting in the X. So when you're in doubt and you're not sure if you actually see whether the atoms are chemically equivalent or not, really, I can't emphasize this enough, go through putting in that X. And this exercise, even if it seems trivial to you, because what we're going to be able to get is information that is not necessarily obvious from elsewhere. So what I want to do now is go through, this is problem 13.13 in your book, or parts of them at least, go through those and do this exercise for a few other cases. So if I look at this molecule shown here and these two H atoms shown in red, I want to know if these are chemically equivalent. So to do so, I'm going to swap out each one with an X, and then ask myself if the molecules that I get from doing that swap are the same or different. So these are the same, these are identical. There's no chiral center elsewhere in the molecule that would change things. No, wait, hold on. Are these the enantiomers? Okay, I lied. These are not identical. These are actually going to be enantiomers of each other. Again, so if I put in the chirality here, if I have this H coming towards us, this H coming towards us, and that H going back into the board, I now am generating chiral centers here where the X is either back or coming out towards me, and therefore these two protons shown here in red are going to be enantiotopic. Now if I look at this molecule here, I'm going to go through again, always go through the same exercise, and here we're going to put some chirality into the system as well. If I go here like that, and I replace each one with an X sequentially, and then ask myself, what do these molecules look like? Well, here we already have a chiral center in the molecule. That's this guy over here. I know this is a chiral center because it has 4 different things attached to this carbon, this H, this OH, and the ring going around. Oh no, wait, I lied again. Sorry, guys. This is not a chiral center. Alright, so let's just be clear on that, because if I go around the ring this way, it's exactly the same as if I went around the ring the other way. So this, again, is not a chiral center. That's just designed to confuse you. In which case, we're left with the same situation that we had in the previous example, that replacing the hydrogens on the same carbon is going to lead to two different enantiomers. Again, enantiomers and not diastereomers. I think, I hope. In which case these are enantiotopic. Because this is not a chiral center here. You're going to create two chiral centers. Okay, maybe I'm wrong. All right, guys. Or diastereotopic. So here, I'm going to give you another chance to get up to 3 points extra credit if you can explain to me which one this is. Is it enantiotopic or diastereotopic? And I need a coherent explanation. And it has to be sent by email by 8 a.m. on Friday. By email by 8 a.m. on Friday, that's February 6th. Alright, I hope that's clear for everybody. Now let's do 2 more examples to figure out whether these compounds are whether these hydrogen atoms are chemically equivalent or not. And I'm focusing in particularly on this alkene, so this is an interesting, sort of a different case than the sorts of things we've been looking at until now. And here I'm going to replace each of these again with an X and ask myself, what relationship do these two things have to each other? So here, in this first case, what I have is the X is on the same side as the H. Here I have the X on the different side from the H, so these are clearly not the same. What I'm getting are diastereomers. Diastereomeric products here. Right, these are stereoisomers that are not enantiomers, which means that the protons in question are diastereotopic. Do one more example, shown here at the bottom, where I'm looking at these two protons here, starting with the chiral center in the molecule, so that should automatically be obvious to you guys. This carbon is a chiral center because it has 4 different things attached to it, which means that these protons, which in general would be enantiotopic, are going to end up being, in this case, diastereotopic. So I hope in general that doing these problems is helpful in this particular exercise, because it's not altogether obvious what relationships two hydrogen atoms are going to have to each other, but once you start replacing them each with an X, then hopefully that gives and makes things clearer for you.